All right, well, we've been steadily getting smaller and smaller in spatial scale, and we're now kind of also on the frontier in new discoveries. So extrasolar planets are a very new phenomenon. So what this plot shows is over the last 20 years or so, the rate of planet detection versus mass. And so in the past year, we now know about Earth-sized planets orbiting nearby stars, and we've sort of steadily progressed downward in mass. And at the same time, we found a huge number of objects. So this is sort of a summary diagram that's showing what's been found so far. This is a logarithmic period scale. Earth and Venus are here. Earth has a period of year, of course. Jupiter is out here at a period of a little bit more than 10 years. And then these are the mass of the planet divided by the mass of the star that it's orbiting. And in that framework, you can also plot the Jovian satellites, thinking of the moons of Jupiter, for instance, as a set of extrasolar planets. Earth's moon falls up here in this part of the diagram. And so what's interesting is that there's really three major groups of planets that have been found so far. Giant planets with eccentric orbits, of which Jupiter appears to be a member. A population of hot Jupiters. These are Jupiter mass planets with periods of less than a week. And an enormous population of planets that are completely unexpected and which are completely alien to our own solar system. Planets that have masses less than the mass of Neptune and orbital periods running for days to weeks. Another remarkable thing is that we're starting to get physical information about the planets. And so this is a plot of densities versus planetary masses. At large mass, you have Jupiter-sized planets which get steadily denser and denser because of the degenerate relationship. Jupiter is at the edge of electron degeneracy, and so these objects don't get larger as they get more massive. You reach sort of a minimum density, and then you go through this region that was completely unknown. The largest mass gap in our own solar system lies between the Earth and Uranus. There's no planets in that gap. And it turns out that the planets in that gap vary in radii or density by an enormous amount. If you have a planet that's 5 times the Earth's mass, you have literally no idea what its radius is going to be. It could be an Earth radius. It could be a Jupiter radius. This is a completely interesting but completely unsolved problem and a total surprise. And so that kind of brings up the issue of, can you do interesting large-scale calculations involving extrasolar planets? And this is a theme of these remarks is sort of that it's going to be difficult, not because the computers aren't up to speed, but rather because the amount of information that we have to compare with is really extremely limited. This is a graph of, over the last 20 years, the improvement in weather prediction. And what it shows is that from 1989 to 2011, we've gone from being able to usefully predict the weather 6 days in advance using a certain statistical criterion to usefully being able to predict the weather 8 days in advance. And there's been just a colossal improvement, as everyone here knows very well, in computational power. But most of this improvement in our understanding of the Earth's weather system over short time scales actually comes from just having better initial conditions. We've got much better monitoring of the oceans. We've got much better, radio sondes and information coming in instantly. And so this improvement is due to a small extent to orders of magnitude and computational improvement, but it's mostly just due to better initial conditions. Exoplanets, in some sense, are just a fantastic exascale problem because they really involve everything, I think, that Mark talked about and more stuff. Fully 3D MHD is required. Extrasolar planets, a lot of them are right in the area where resistive MHD is most interesting and most important. Many of them are on crazy eccentric orbits where you have 1,000-fold variation in the amount of light that's being received. Objects are rotating, they're convective, frequency-dependent radiation transfer is key, non-equilibrium chemistry, the list just goes on. And so codes certainly can be built to do those kinds of things, but the real question is, when you have an extraordinarily nonlinear system that's sensitively dependent on initial conditions, and you don't have much to go on whether there's any use. So because it's challenging and exciting, this is something that's being done quite a bit. There's a lot of simulations that look at the surface flows and the weather patterns and the expected meteorology on extrasolar planets. Perhaps the most famous extrasolar planet was the first transiting planet, HD 209458. This has been known for well over a decade now. And so this is just, I took 2 AstroPH reports from state-of-the-art simulations from 2002 and then state-of-the-art simulations from 2014. And during that 12-year period, of course, there was a huge increase in the number of physics and the computational resolution, and all the bona fides for these simulations were massively improved. So the question is, has there been an improvement of their characterization of the planets? And if there has been, can you even tell? These planets, like the one on the previous slide, that are most often simulated all fall on this part of the diagram. They all are very hot planets, hence they can be observed in the infrared, and they're all roughly the size of Jupiter. And the ones that are most interesting are the ones that go behind their parent star as seen from Earth. And so with the infrared space telescope, when a planet goes behind the star, you can, through difference spectrometry, figure out how much radiation is coming off of the planet in different frequency bands. And so the sort of 0th order weather report from a planet is to ask, how hot is it on the day side, integrated over the entire day side, in comparison to the night side? And so if a simulation has any, global simulation has any merit at all, it should be able to tell you whether it's hotter on the day side than on the night side. And so what's interesting, but also a little depressing, is that when you take all of the available observations of extrasolar planets and look at their temperature measurements and try to get their day side and night side temperatures, it's all over the map, and there's literally no trend. And so you don't know, if you make a simulation of a particular planet, you don't know whether the work that you're doing has any connection to reality. And in fact, the total sum of the observations, when you histogram them up, makes a remarkable Gaussian curve, which is suggesting that the central limit theorem is at work. An optimist would say that the central limit theorem is at work in the sense that there's many different physical properties that are causing a planet to be either redistributing its heat or not redistributing its heat. A pessimist would say that there's many different sources of error in the observations and analysis which are combining to give random results. But at the end of the day, it just turns out to be an extraordinarily good Gaussian curve, and so it's completely meaningless to compare any given exascale or petascale calculation to the observations that we see. So that's a bit of a sort of a bummer, because it would be exciting to do these large-scale simulations. We can adapt fluid dynamics codes that are used for weather prediction here on Earth. It would be very, very exciting to do that for extrasolar planets. But if you do that, it will look good, but the results are really meaningless. The other interesting problem is how the planets form. For years and years, given talks, or people have given talks that show that the fraction of stars that have a protoplanetary disk declines quite rapidly after the stars form. In general, protoplanetary disks from which planets form are gone within 5 or at most 10 million years. And the new, very significant and exciting point here is that disk dispersion in a few million years, that's been known for a decade, and more often than not, they leave planets behind. The results of the Kepler survey and the results of the radial velocity surveys show that more than half of the planets in the solar neighborhood have a Neptune mass planet or less with a period of 100 days or less. It's the default mode of planet formation. That's what, not just what sometimes happens, but what generally happens, more often than not happens. And so the question is, it's a fact that these planets are being left behind in most cases. It's a fact that planet formation is not particularly well understood. And it's my opinion that large-scale computations can offer modest insights into trying to understand what's going on here. My time is running down, so I'll just show one or two more slides. A huge chunk of the problem can be sort of encapsulated in two different separate issues. Something that's remarkable is that, you know, on different spatial scales ranging from the planetary to the galactic, there's many, many orders of magnitude in size scale. But Saturn's rings, a protostellar disk, and a disk galaxy share a large number of commonalities. And in particular, they're all self-gravitating disks that show spiral structure and are right on the threshold of gravitational instability. In the case of the Saturn's rings, the dynamical temperature is so low that even though the rings have a low mass, they show interesting self-gravity effects. The difference between a disk galaxy and a Saturn's rings from the observational standpoint is that we have extraordinarily good pictures of disk galaxies, and we have amazingly good pictures of Saturn's rings. Saturn's rings completely fill the field of view for Cassini. A disk galaxy subtends a very large portion of the sky, and so you can see what's going on, and that can inform your simulations. ALMA is a very exciting capability, but even with ALMA, our ability to see what's going on in protostellar disks, to image them, is catastrophically less. Protostellar disks subtend a few arc seconds in the sky. Another problem is the number of dynamical times that are involved. So a disk galaxy in the outer regions, the sun has gone around 45 times or something like that. If you want to understand evolution of a disk galaxy, you're interested in simulating tens to hundreds at most of rotation periods. Saturn's rings are on the totally other end of that scale. The Saturn rings particles have gone around Saturn about 1 trillion times. But because of that, steady state has long since been established. And so computations that seek to understand Saturn's rings are similar to computation that seeks to compute the weather 5 days from now. You know the starting conditions extremely well, and you're interested in tiny departures from equilibrium. In the protostellar disk, you have a complete reorganization of the system, but that reorganization takes place over 100,000 to 100 million orbits. And so a hydrodynamical calculation that tries to look at that process, if it's Courant limited, just simply isn't going to work. So I think I've talked enough about challenges, so I'll skip that slide. There's lots of challenges, and I'll end with this comparison slide from a completely different area of science. This picture right here is from 1875, and it was from Joseph Haeckel's book talking about evolution. Evolution at this point was a new concept. It was the right concept, but the ideas were a little bit naive. And so you have man sitting up at the top of this tree, and the entire tree of life involves bats and beasts of prey and snakes and sort of charismatic large animals that you can see with your eyes. Whereas when we look at the modern tree of life, all the stuff that's in Haeckel's tree of life is kind of buried right up here, and we see that the real interest and the real diversity is occurring at the molecular scale. And I think we're at a similar state with our computations of extrasolar planets, in the sense that there's a few charismatic planets like the Earth, hot Jupiters that we know about and can find some things out about, but the true diversity and the true interest is still a problem for the next century, in the sense that molecular biology was a century ahead of when this tree of life was made. So I'll stop there.